Good morning to everyone. I am Dr. Muriyasan, Department of Computer Science. Today my lecture is on digital electronics. All the computers can perform only with digital. Previously analog systems are available. The analog in the form of the continuous variables or changes. So to avoid this problem, digital systems are arises. So digital, all the computers is based only on the digitals. All the computer language are designed with the help of digital systems. In this session we are going to discuss about digital electronics, especially in counting in decimal and binary, place values, binary to decimal conversion, decimal to binary conversion, and then corresponding its electronic translator, hexadecimal numbers and octal numbers. So in this part, counting in decimal numbers, decimal and binaries, number systems. There are four types of number systems are there. Code using symbols that refer to a number of items, number systems, decimal number systems, that is 0 to 9, binary number system 0 and 1, octal number systems 0 to 7, hexadecimal number system 0 to 9, and A, B, C, D, E, F. There are 16 number systems are available. Above mentioned 4 number systems. Each number system have its own base numbers, depends on the total number of numbers. So first we are going to discuss about decimal number systems. In the place of decimal number systems, it contains 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 symbols are there. Its base value is 10. Like that, binary number system consists of only 2 numbers, 0 and 1. It totally consists of 2 numbers. That's why its base value is 2. All the computer systems are designed only with the binary number systems. And then place values, numeric values of symbols in different positions. See the example, place values in binary number system. The rightmost is 1, and the next number is 2's, and the next number is 4 and 8's. For example, the given number, the values are 1's position is 0, 2's position is 0, and 4's position is 1, and 8th position is 1. So we consider the corresponding values of the place values. 1's 0, 2's 0, 4's 4, and then 8th position is 4. Then totally it is 8 plus 4 plus 0 plus 0 is equal to decimal 12 values are there. And then followed by the cases, the same conversion from binary to decimal conversion. The number is 110011. The conversion is made. 1 is equal to equivalent decimal value is 1. Another from right to left, another value is 1, corresponding weightage is 2, and then 0 position 0, and then another one is 1 with corresponding weight 16, and then 32. So the totally the given binary value is equivalent decimal is 51. And a simple example for the cases from binary to decimal. The binary numbers 1001 is equal to decimal value 9. Like that, binary value 1111 is equal to 15. The same binary number, it is also called hexadecimal in F. And then another one is 0010 is equal to 2. So now we have to discuss about decimal to binary conversion, how these things are happened. This is called as double method. with the help of using divide by 2 process. For example, the decimal number is 13 divided by 2 is equal to quotient is 6 and then remainder 1, again the quotient again divided by 2. So we can repeatedly divide by 2. 6 divided by 2 is equal to 3, remainder 1, and then another number is remainder 1 and another is remainder 1. So totally from left to right 1 0 1 1, this is equal to the decimal number is 13. And then another cases examples, decimal number 11 is equal to 1011, decimal number 4 is equal to 0100, decimal number 17 is equal to 10001. And then what are the devices are used to convert this part. So the devices that convert from decimal number to binary number and from binary to decimal numbers are takes place with the help of using two devices. The device's name is encoder and decoder. Encoder translate from decimal to binary, like that decoder translate from binary to decimal. These are the devices or conversions. And then electronic encoder decimal to binary, how does it takes place? So in our decimal input we can press 3 and then the part is there, decimal to binary encoder that convert equivalent what is this binary number that transfer. The encoders are available in IC form, integrated circuit form. This encoder translate from decimal input to binary, that is BCD output. We can reach your output. And then like that in our electronic decoding, that is binary to decimal, given binary number and then transfer to binary to 7 segment decoder. Corresponding driver is there, that signal is transferred to output. We can get the decimal output. So the last one is LED form. LED, you can be able to visibly see the normal decimal numbers. Electronic decoders are available in IC forms. This decoder translates from binary to decimal. Decimals are shown and as and 7 segment LED light emitting diode display. This decoder also drives the 7 segment display. And then hexadecimal number system. As I already mentioned in the earlier stage, use of 16 symbols are used. Its base value is 16. And then as in the place of decimal 0 to 9, and then apart from that another number A, B, C, D, E, F. So this is a corresponding decimal number, binary number and hexadecimal number. For example, if 10 decimal number 10 binary equivalent binary number is 1010 and then equivalent hexadecimal is A. And then like that hexadecimal and binary conversion. So this is an example for hexadecimal to binary. Hexadecimal 3 equivalent to, because hexadecimal is 2 to the power of 4 is equal to 16. 2 to the power of 4 equal to 16. So the given hexadecimal number automatically converted into 4-bit binary number. That is your conversion. Hexadecimal to binary. 3 is equal to 0011. C is equal to 1100. Like that, binary to hexadecimal, the same conversions are applicable. And then decimal to hexadecimal conversion, the process takes place 640. For example, decimal number 47 divided by 16, the quotient is 2, the remainder is 15, the remainder 15 is equal to F, and then quotient 2 divided by 16, so 0 quotient and then remainder 2. And like that, the hexadecimal to decimal conversion, the same cases are applicable in this part. Place value is 256, 16 and 1s. 2 into, that is actually in the place of hexadecimal number, 2 to the power of 16 power of 0, 16 power of 1, 16 power of 2. 16 power of 2 is equal to 256, 16 power of 1 is equal to 16, 16 power of 0 is equal to 1. So the conversion is equivalent B for hexadecimal and then D for hexadecimal, 2 for hexadecimal number. The conversion from left to right, 1 into 11, because B is equal to 11 value and D is equal to value of 13 and 2. So we can multiply all these things and add the value. Finally we can get the number 731. So this is another example for convert hexadecimal to binary number. A is equal to equivalent binary number. Convert hexadecimal number 16 to decimal. Like that, convert decimal 3 to hexadecimal is equal to 3m. 16 is equal to 22, A6 equal to the binary numbers. These are the 3 conversions are considered. And then finally, one more number systems are available, that is octal number system. The values are 0, 1, 2, 3, 4, 5, 6, 7. So the base totally it consists of 8 numbers. The base value is 8. That is the given decimal number, equivalent binary number and octal number. Okay. And then at the end, the practical suggestion on number system conversions: use a scientific calculator. Most scientific calculator have decimal, binary, octal and hexadecimal mode and can either convert between codes or perform arithmetic in different number systems. Most scientific calculators also have the functions that are valuable in digital electronics, such as AND, OR, NOT, XOR and XNOR logic functions. Thank you for listening. Digital electronics. Thank you very much.